Okay, so today we're going to do some review. And we're going to draw these compounds. So I'm going to give you like 10 minutes to draw these compounds. Compound, yeah. Still recording. CH4, NH3, H2O, CO2, NOF, NOF, and CH2F2. So go ahead and draw those. We want what? Formula, name of the shape, bond angle, polar, non-polar. Okay, go. And we're back. All right. We already did the first two because we got so excited we forgot. All right. So there's CH4, AX4, tetrahedral 109.5, non-polar. NH3, AX3E, 107.3, trigonal pyramidal. Polar because, of course, it has lone pair right here on the central atom. Right. As soon as you put lone pairs on that, E on the central atom, as soon as you have E in the formula, it's polar. These are all X's, and these X's are all the same. So that's an H, 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 and H, so therefore non-polar. Perfect. All right, we're all cut up here. Look at us go. What's next? H2O, we'll do that one. Who's gonna, oh, Jade is doing this one. Yeah, you. Uh-huh. Like that? Right, okay, and what's the formula? Okay, perfect. R2D2, C3PO, Chewbacca. By tomorrow. Yeah. Bond angle. Perfect. Shape. Tetrahedral get bent. And polar, yes, absolutely polar. Water's always been polar. It's always going to be polar. And we got E on the lone, or E on the central atom. Of course, we have two of them actually, so most certainly polar. Okay, good. I guess I was taking a break to do diagram. Let's just keep going, I guess, and I'll go back to that. Who am I gonna pick on? Who wants to volunteer the next one? Yeah. Yeah, okay. Yeah. Like that? Yeah. Yeah. Holy dynamite. And non-polar. Okay, and it's AX2 and the X's are the same, so non-polar, yes? Okay, good. Linear is the shape there. If you can't read that, linear, and 180. Good, perfect. And that's what? How many more do we have? One more? Two more? One. What's the next one? Who else wants to do one? Pick one. I'll start. Anna, perfect. Thank you for volunteering. Oh, NOF. I like to say it's NOF, or fawn backwards. As in this class sure is fawn. That was a stretch. All right. Okay. Okay. What else does Zen have on it? Anything else? Lone pair. Okay. So all said and done, we probably should have a little something like this. Yes? Okay. What's this one called? Trigonal planar bent. Oh, that's not even a T. Let's try that again. I don't know what that is. Trigonal planar. And for this one, you will need to put trigonal planar bent. If we, like I said before, I think I mentioned this, but if we were just talking about bent, it's probably tetrahedral because that's the most common one. Trigonal planar bent. What else here? A, X2E, and 120. Okay. Polar, non-polar? Absolutely. It's got E in the general formula. It's most certainly going to be polar. Okay. All right. And last one, CH2F2. Is that right? Yeah? Who's doing that one? Come on, somebody. Yeah. Okay. Sounds good. And you don't have to have it like that. You decide whatever, as long as you got AX, like this C's in the middle, obviously, and the whatever you want to do is fine with me, as long as what's the formula here? Yep. Well, what shape? Well, you said you were going to do it. Yep. Tetrahedral, what's the bond angle? 109.5. Polar and non-polar? We did this one in class the other day. Polar. Okay. Are all the x's the same? No. And I know it looks like they cancel out, but they don't, right? Okay. So I showed you CH4. I might as well record this. I don't know why, because, hey, look, everybody, it's CH4. I guess this would be better with live streaming, I guess, or something. CH4. I'm going to jump to CH2F2 if that's okay, because I got this one here anyway. And I think we talked about this last day. Remember, it doesn't really matter where you put those atoms on. We have to remember it's three-dimensional, okay? And again, I think we talked about this last day, didn't we? Or no? Did we with this? Remember this? No? Yes? Yes? Okay. So remember, we talked a little bit about vectors, right? And we're going to have a pull this way and a pull this way. And so the net resultant's going up here, basically is what the net resultant is, and you don't have to worry about that. That's physics stuff. And actually the pull here is this way and this way, yes? So the actual pull is into this atom here. So we're probably going to get a very negative end to this atom, or to this molecule, I should say, and a very positive end to the molecule, yes? So negative and positive, and we'll talk a little bit about that coming up today here, okay? What that means. But this is polar, okay? Polar. And it doesn't matter where you put the F's, you're not going to get them to across from each other. It's not going to happen because they're not across from each other, okay? What is another one? I need to do NH3, yes. So N, just so you know, looks a little something. This is nitrogen here, and NH3, let's see, use these little ones here. I'm going to need some H's. H's are the white little things here. No, almost lost all the hydrogens there for a second. That would have been bad. All right. There's nitrogen, NH3, okay? And we need a lone pair on top, yes? So that looks a little something like that there, okay? So you can kind of see it's actually a little different shape to it, isn't it? It's kind of a little flatter. It's shrink down a little bit here. So when you look at that compared to, I guess, this one here, okay? I know this is not great, but I used to put these on desks, but now we can't do that anymore. But you can kind of see it sits down a little bit more, okay? But that's kind of the difference here. Now remember, this lone pair, what do the lone pairs do? This is a lone pair right here, okay? This is not a paddle, miniature ping pong paddle for the atoms, okay? Smash. Okay, that's funny, come on. Hey, that's, no? Nothing, eh? Hey. I don't know why I'm recording. They can't see anything anyway. Let's just pause it. Today, so people have something to do at home. All right, so today, lesson 14. We talked about network solids really briefly yesterday. I said, don't worry about that. I don't really care about that. But, you know, again, carbon to carbon bonds can be arranged in different ways. We got pencils in one way. Under some extensive pressure and heat, we get diamonds, which are apparently some people's best friends, is what I'm told all the time. And diamonds, of course, are incredibly hard, very packed together, of course, yet pencils are pretty weak. People always ask me, can you make diamonds out of pencils? Probably, I guess you probably could. Yeah, as long as you have intense heat and pressure. I don't know about pencils, but out of coal, yes. Carbon, yes. Okay, moving on here. We talked about intra yesterday. So we talked about intramolecular bonding or forces. We talked about inter. I think we talked about those notes. And just a reminder here, it basically says this. And maybe this is a bad example, but for example, in this case here, this would be intra, what holds one molecule of sugar together, covalent bonds, yes? Those covalent bonds are pretty strong. It takes a bit of heat a bit of energy to break these into carbons and hydrogens and oxygens, okay? So the first thing that would happen, of course, is we would take this sugar molecule. It would break into sugar liquid because, of course, we'd have another C12H22O11 here and maybe one more here, okay? And what we're going to talk about today is there is some kind of bonding that exists between molecules. That's intermolecular bonding or intermolecular forces, okay? There's some kind of force or bonding nature there. So the first thing that would happen if we start to heat this up is we would get from a solid form. By the way, that means that these bonds are pretty strong because they're holding together. We'd break a few and we'd get a liquid form. So we'd break a few of those bonds, those attractions, and we get a liquid form. And then if we continue to heat it up, we'd possibly get to a gas form. And then if we continued to heat it up, we'd eventually get to carbons, hydrogens, and oxygens, which would be decomposition, of course, okay? But to get it into decomposition, to get those covalent bonds to break, you're gonna need some energy for that, okay? That's gonna take some energy, all right? It's gonna take some heat, all right? Now, we're gonna talk about what are these forces here? What are some options between those? Different molecular compounds have different types of forces. We need to know, hey, if we got CH4, what kind of force is that between the two? If it's HCl, what kind of force do we have between molecules? What's holding them together? What if we have water molecules? Why do water molecules form a little bubble? Cohesion, adhesion, you'd say yes. But in Science 10, you actually took the correct term for that, which we call what? Do you remember? Hydrogen bonding is the correct term for that. Okay, what is hydrogen bonding? We're going to talk about that today. Okay, so here we go. First one, I'm going to let you copy. Okay, right there. Yeah, dipole-dipole. Now, so dipole-dipole is our first one that we're going to look at. We have three, like I said. This is one of them. It says in polar molecules. So that's important for us. If it's a polar molecule, this is an option. Okay, we actually have another option as well, which we'll talk about, but this is definitely an option for polar molecules. We know that in polar molecules, I showed you a couple today, we have a negative end to the molecule and a positive end to the molecule based on differences in electronegativity, of course. Because these molecules have a different poles, or a negative end and a positive end, they're called dipoles. When any of the two dipoles are close enough to each other, they will attract one another, okay? So anytime those two dipoles, maybe a little bit of a negative end of one molecule and a little bit of positive end, they'll attract each other, okay? All right, so our example here is HCl. This would apply to other ones that we draw tomorrow that happen to be polar as well. Not all of them, but just this could be the force tomorrow that we'd be drawing, okay? But again, it just depends on, we got two things to talk about here. But HCl, I just picked it because it's super easy, okay? This is not an AX2 or AX3 or anything like that. I just picked this molecule because HCl, okay? And of course, we share some electrons. This is 2.2. Remember, how do we decide if molecules are polar? Well, or non-polar for that matter. We look at the general formula, AX2, AX3, AX4, or AX2E, AX3E, whatever. But in this case, we don't have that, so I just kind of look at the difference in electronegativity here. And help me out here. I think chlorine's 3.2, is that correct? Okay. So which one is the partial negative? You need to know this for the test. What is it? You get 1 mark already if you know this. Partial negative is which one, H or Cl? Come on, give me all you got. That's a movie. It's one of my favorite movies of all time. What is it, H or Cl? Which one is the partial negative? This is not a tough question, people. Oh, give it to me, come on. Yeah, yes, thank you. The higher electronegative one is the partial negative, yes. Look, you got to pull on electrons, yes. Those are your two options. Who wins the tug of war? Electronegativity, by the way, is the ability to attract electrons, yes? What was your quiz answer yesterday? So we're pulling electrons that way. This leaves this a partial positive, yes? Okay. And of course, we probably don't have one HCl, we have many of them. And so we have an HCl here, same thing. This is a partial negative and a partial positive. Maybe we have one down here, partial negative, partial positive, and we have all these HCl's here. And right here, that attraction there, that bond, that temporary bond, if you will, or not a temporary bond, but that attraction, if they're close enough together, that is what we call a dipole-dipole force, or that's the intermolecular bonding or force of dipole-dipole. Okay, and again, if you remember in the notes, it says basically if you had like two of them, you're probably not going to get a lot of attractions there. But if you have billions and millions of them, it's that one that we took in the, it's supposed to be like this, but I can't draw that. Delta. Okay, but I just do kind of like that thing. It's not a, it's more of a D. It's the music note. You take music? Think perfect. All right, there you go. Music note. Yes. Okay, so partial negative, partial positive, yes? And again, we could have many attractions. So perhaps this one here, if these are close enough, there could be an attraction there. If these are close enough, this could be an attraction here. How strong is that? Well, it depends on some factors, which we're going to talk about, okay? Now, this is for polar molecules. This is one option for polar molecules. That's what it kind of looks like, okay? Again, those molecules have to be close enough, and there has to be that attraction in order to take place. Now, if that attraction is quite strong, okay, we're going to learn this. Intermolecular forces are responsible. We actually already should know this. Intermolecular forces are responsible for what? What? Think back to our first example today, sugar. Yeah. States. Yes. States for molecular compounds. What's the state of an ionic compound? We already know this. This is review. Solid. Yes. Because it sticks together, really opposites attract. What about metals for metallic bonding? Usually the states are what? Solid. Yes. Except mercury. What about molecular compounds? It depends on that intermolecular force. How strong is it? Sugar, it's a solid. Okay. Water is a liquid. HCl is a gas. So how strong is this? What would you say if this is a gas? What would you think? Probably not very strong, right? Right? Because they're not holding together particularly well. Okay. Does that mean that dipole-dipole is weak? No. What it means is for this particular molecule, it's not very strong. That's all. We'll get to that. Okay. So that's an example of dipole-dipole. Kind of looks like this. If you ever see this, basically you'll see an arrow kind of pointing in a direction, and you'll see a positive sign at the other end. Well, this is your H right here. So this would be your positive end, and this is your negative end. So the electrons are getting pulled that way. And again, you know, the more molecules you have, the more attractions you can have, the more of these intermolecular forces you can have. In this case, it would be dipole-dipole. So this is a dipole-dipole here, 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 there, there. Between molecules, okay? So you can see there, what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 molecules of maybe HCl, I'm not sure, it doesn't say. 12 molecules of HCl, how many attractions do you have? Lots, yes? And the more molecules you have and the more attractions you have, the more chance we have of changing it from a gas to a liquid or a liquid to a solid, yes? Okay? All right, so we'll talk about what that kind of looks like. But intermolecular forces are, you have to know this, are responsible for the states. States basically is a fancy way of saying melting points and boiling points, yes? Because if we have a melting point, it goes from a solid to a liquid. If we have a boiling point, it goes from a liquid to a gas, yes? They all mean the same thing. That's what we're doing for the next 3 lessons, basically. All right? The next one is called hydrogen bonding. This one's a little more complex, okay? So I'll let you guys copy that, and then we'll talk about that briefly here. We'll start here. I'd like to get this one done before the end of today here for sure. Okay, so Hydrogen bonding is the next type, so this is the second one that we're going to talk about. And I think we have to know this. It's a specific type of dipole-dipole. So again, what kind of molecules are we talking about here? Polar or non-polar? Dipole-dipole is what kind of force? Polar, right? So this is also for polar molecules. It has to be polar. But it's a very specific bunch of polar molecules. It says here, when a hydrogen atom is bonded to a highly electronegative atom, such as oxygen, nitrogen, or fluorine, the electronegative atom draws the electrons away from the hydrogen. Since hydrogen only has a bonding electron, it leaves a positive proton in the nucleus nearly bare. So I'm going to draw that for you. But we have to keep in mind, now, it has to be H bonded to one of those three atoms, okay? It has to be an H bonded to one of those three in order to have hydrogen bonding, okay? And we'll talk about the little nuances here. It doesn't matter how many times that happens, as long as somewhere in the molecule, somewhere, there's an H bonded to an O, an H bonded to an N, or an H bonded to an F, okay? As long as there's that somewhere in the molecule, we will have what we call hydrogen bonding, okay? Okay, I'm going to let you copy this as well, and then we'll talk about it. A hydrogen bond is the electrostatic attraction, basically the opposites attract, but again, it's the partial opposites attract, right? The partial positive, partial negative. Exposed proton of the hydrogen atom and the partial negative charge on the highly electronegative atom, such as usually oxygen, nitrogen, or fluorine, on a different molecule. Lone pairs will enhance that ability to attract other molecules as well. So when we take a look here, our example will be HF. It's a nice simple one. It's another example of hydrogen bonding. Very famous. We already talked about it today, so you should know because I already said it. What is it? Just yell it out, people. What's a famous example of hydrogen bonding? Water. Yes. Okay. Here we have, I just went with this one. We could do this with water as well, but it's obviously a little more involved because I got to draw the whole tetrahedral bent and all that stuff with the lone pairs. But here's an example, HF. Okay. HF, that's hydrogen bonding, right? H is bonded directly to F. H bonded to N, H bonded to O. Okay, those are your options. Well, here's HF. Okay. And again, hopefully we understand this is 4.0, this is 2.2. By the way, this is very, very, you could almost make a case that this would be, if you put this in water, it's most certainly an acid, yes? I mean, you're going to get H plus ions for sure. I mean, this is very, very polar, isn't it? I mean, this is on the verge. The difference is 1.8 here, right? What's the cutoff? 1.7, yes? So this could almost be ionic in a way, okay? But we'll just go with molecular. This is the partial negative end, and this is the partial positive end. But what do you really have when you talk about H bond to F, or this H bond to a highly electronegative atom? Well, remember, the pull this way is a lot. The pull this way is not that much in comparison, right? I mean, that's an exaggeration there, but like there's a big difference here, yes? Okay, so what happens is we talk about sharing these electrons. That's called a polar covalent bond, okay? Because we're not sharing the electrons equally, are we? Very not equally. Very, very not equally, yes? Like the extreme of not equalness, okay? So electrons are going to get pulled over to this F here. So if I kind of did, I'm just going to do this, I think, just for simplicity's sake, okay? And here's my H. Now remember, H has one proton and one electron, yes? Well, if that electron is spending more time over here, that leaves basically this one proton here in the nucleus, okay? Pay attention. Not put your phone away. H has got one proton in the nucleus. That electron's getting pulled towards the F. So we get a very negative end, okay, and a very positive end. So I kind of like to describe it like this. Look, we have the partial positive and the partial negative from the difference in electronegativity, yes? But we also, what else do you have right here? Well, you have a very positive, and you want to write this down, end, you have bare positive nucleus and the partial positive end. Okay, I'll say that again. This is a very positive end because you have the bare positive nucleus, positive proton in the nucleus, and you have this partial positive here as well. So you can kind of think of it as double positive, okay? Basically kind of very positive. And that's that end of the molecule. So very positive end, you get a bare positive nucleus and the partial positive end there. Okay, copy this down. Don't be shy. Over here, on this end, what do you have there? You have a very electronegative atom, okay? So it's pulling electrons towards it. Very negative end. High En, okay, which pulls electrons towards it. You have the partial negative end. Okay, so you're getting that very partial negative end. High electronegativities pull with a greater force. And in the notes it says lone pairs enhance that end. Lone pairs enhance that end. So not only do you have high electronegativity, partial negative end, we also have the lone pairs on that very electronegative atom. Okay? Now, are you always going to have lone pairs on the highly electronegative atom? That, I guess, is the next question. Should I even put that down? Does F have lone pairs on it? Yeah. What's the other option? Does N have a lone pair on it? Yeah. Does O have lone pairs on it? Yeah. So we're always going to have those lone pairs that enhance that. Okay? They're always there. So not only do we get very negative end here, high electronegativity, partial negative lone pairs enhance that. Okay? Now what happens is, by the way, this is not hydrogen bonding. Okay? After all that, we still do not have hydrogen bonding because hydrogen bonding has to be what? If you can tell me this, I'll let you stop for the day. Oh, almost. Hydrogen bonding is what? I still haven't shown you hydrogen bonding here. What's the last part? Yep. Yeah, what does that mean? Yeah, between molecules, yes? So this is kind of how it's set up, but I technically will need another HF here. Partial negative, partial positive. Very positive end. You don't have to put the brackets there. Very negative end, okay? Hydrogen bonding is that link between very, very polar molecules here that, like we just talked about, right there. That's hydrogen bonding, okay? Between molecules. The very, very negative end of this molecule attracted to the very, very positive end of that molecule. That is hydrogen bonding. Okay? The link between those two. Okay? Now, how strong is that? Do you think that this is stronger than dipole-dipole or weaker than dipole-dipole? What do you think? You should know this by what we've taken today so far. What do you think? Stronger or weaker? Stronger, yes? Because it's very, very negative, very, very positive. So if it's stronger, what does that mean for states? Does that mean that this should be ramped up? Remember this one here. By the way, look at the difference between these two, by the way. Before you pack up, just relax. You got time. You got 6 minutes. HCl. We said that that was a gas, yes? So what does that mean for this one? Does that mean that this is strong enough to change it from a gas to a liquid? Because that's what we're talking about here. How strong is that intermolecular force? And the answer is, believe it or not, No, it's not. Is it stronger? Absolutely. Okay, I'll show you that with a graph. Is it strong enough to make it a liquid? Still not. Okay, so that's why molecular compounds are very hard to predict the states of them. The carbon dioxide we know is a gas. Water is a liquid. Sugar is a solid. You know, we start getting into propane, C3H8. That's a molecular compound. What's the state? Well, that's a gas. C4H10, why is that one a liquid now? Okay. Why is pentane a liquid? Or I don't actually, maybe butane's not a gas or a liquid. But why? How do we get, what side's that? So we need to talk about that still. But this is definitely stronger, but it's not strong enough to make it a liquid yet, at room temperature that is. Okay. It's still a gas, it's still boiled, but we'll talk about that, okay, as we go. But that's how we get hydrogen bonding. Okay. There's an example of water there. Okay. We have the partial negative end of water, which would be the O, attracted to all the H's that are around it, yes, of a different molecule. You have to remember, and this is key here, between molecules, between, those are intermolecular forces. So far, you know dipole-dipole and hydrogen bonding, okay? They're both for polar molecules. That's important there. This one is going to be for nonpolar. Okay, there's only one for nonpolar. So tomorrow on your quiz, you don't have to do this, but eventually we're going to put down nonpolar. The next thing you put down beside nonpolar will be London forces, otherwise known as dispersion forces, sometimes called van der Waal forces. Okay, but there's only one force for nonpolar. Okay, we'll stop there for today. Tomorrow's your quiz, don't forget. So make sure you study tonight, all the shapes, bond angles, all that stuff, right? Make sure you know it's polar, nonpolar.